Colloids. Colloids are also sometimes called colloidal dispersions. And they're a variation of a solution in which the particles are larger than what we've been talking about. So the colloidal particles are small enough that they will stay suspended in the solution. They will not settle out. But they're larger than the solvent molecules, significantly larger. And they will refract and reflect light. They're large enough. So here we see it looks like they're putting soap into the water, and the water's kind of cloudy. It's cloudy because the particles are larger, and so they will obstruct the light and cause the solution to be cloudy. We have also seen cloudy solutions like this when we formed a precipitate. You pour two clear solutions together and it makes a precipitate and it gets all cloudy. That's not a colloidal dispersion, because if you let that solution sit, the solid particles will fall out of solution. They're too large to stay suspended. So a colloid is sort of in between a true solution and a mixture of solids and liquids. Under a microscope, the colloidal particles have this jittery motion called Brownian motion. And that's caused by collisions that they're having with the water molecules. Here's a very brief YouTube video. I think we saw it earlier in the semester, but we'll just watch it again. Pollen grains. So this jittery motion, those are not alive, but they're bumping into water molecules, and that's causing them to jitter like that. It's called Brownian motion. That's really short. No, stop it. So, adding soap to water. We talked a little bit about how soap works. Here's an illustration of a soap molecule. It's got this nonpolar tail, carbons and hydrogens, and this is going to mix well with oils and greases and things like that. And then it's got this ionic head, this polar head. And if you get enough soap in the water, these guys will find each other and they'll circle the wagons. That's what I think of. They'll make these little spheres with all the nonpolar tails pointing in, because those nonpolar tails do not get along well with the water, but they get along great with each other. And then the polar heads will be on the outside. And so they'll make these little spheres, and there's some repulsion between the polar heads of one group and the polar heads of another group. And so they will stay separated, unlike an oil that will just form a separate layer. So these particles are small. They're too small for you to just see with your eye, but they're larger. They're much larger than the water molecules. And so soap and water is actually a colloid, a colloidal dispersion. Other things that form colloids are things like proteins. So milk has protein in it, right? It also has fat in it. And so milk is a colloidal dispersion, where you have these larger particles dispersed. The reason that milk that you buy at the store does not separate into layers is because it's been homogenized. Homogenization makes it homogeneous and causes it to stay homogeneous. If you have raw milk and you let it sit, the cream, the fat will rise to the surface, right? So there are different types of colloidal dispersions. Fog. You see a lot of that in the winter. That's liquid particles distributed in a gas, the air. Smoke is also a colloid. It's solid particles in air. The ash in smoke are very, very tiny particles, and they will stay suspended. They don't just fall out. So both of these are called aerosols. Foams, such as whipped cream, where you have particles of gases, small bubbles of gases in a liquid, making it foamy. Milk is is called an emulsion because we have liquids. You've got the fat, which is a liquid dispersed in the water. The main solvent in milk is water. You can also have solid emulsions. So opals are silica glass that has water dispersed within it, and that's what gives it its really cool appearance. And then there's the Tyndall effect. So here we have two containers of clear liquids, but when we shine this bright light through them, there's a difference. This first one, we can see the light traveling through it, and in the second one, we can't. The second is a solution. The first one is a colloidal dispersion. The particles here are too small for us to see, but they are large enough to reflect the light. And so we see the beam of light passing through. This happens in my house. That is not my house, but I see these sunbeams in my house because my house is very dusty. Who has time for dusting? How can you see the light beams, the sun rays? You're not actually seeing the sun rays, you're seeing it reflect off dust particles in the air. If the air is very pure, you won't see those sun rays coming down like that. Any questions?